Okay, all right. Today we will now introduce some classification models. So the first one we'll take a look at is the Bayes classifier. And so when we do classification, what we're trying to do is we are trying to figure out the class label, right? And so our textbook says, we have these training objects, and it calls these objects, each of these are these vectors x, okay? And we have n of these things, and these vectors x are in d dimensions. So you have multiple kind of values, individual, multiple values associated, and then and each of these objects has some kind of label, okay? And the label we're going to call T, our target label. And the classes are just some kind of category, right? And right now they have integer labels, but they are categorical variables. Okay, and the goal is to predict the new, whatever class we have. If we have a T new for some figure out the new class for some new object x, okay? It's important that even though they look like numbers, okay, even though they are integer labels, they are categories. And so if you have something that's labeled 2, it's not twice as big as label 1, and there's no meaning to having, decimal values. Like, you can't take the average of these things and get like a 2.5. That's not something that's meaningful, right? It's kind of, if you have different flavors, okay, if you have like label 1 is vanilla, label 2 is chocolate, and label 3 is, strawberry, okay, you can't have a flavor in between, right? And it's not like if label 3 is strawberry, it's not like chocolate is the average of strawberry and vanilla or something like that, which is what it would be if we do treat them numerically. Okay. So in today's lecture, we'll look at the Bayes classifier. And the way we use the Bayes classifier is we use Bayes' rule to find the probability that an observation belongs to a certain class. It's a probabilistic classifier, and so it's going to return probabilities. And if you have, let's say, 3 class possible labels, like label A, label B, and label C, then what the Bayes classifier will return is a vector of probabilities that will add up to 100%. So if you have ABC, you might get probability 19%, 80%, and 1% to add up to 100%. Okay, logistic regression is another example of a probabilistic classifier. There are other types of classifiers. We have these like hard classifiers, which don't return a probability but just a categorical label. So, for example, k-nearest neighbors, support vector machines. These would be kind of hard classifiers. Okay, and the Bayes classifier uses Bayes' rule. This is not Bayesian statistics, so that's something entirely different, where you're treating kind of your unknown parameters as random variables. That's covered in a different course. Okay, so just to review, Bayes' theorem or Bayes' rule is that if you want to find the probability of A given B, you can find it by finding the joint probability of A and B, which can be found by probability of B given A times the probability of A. That's the same equivalent to the probability of the intersection of A and B, or B and A. Okay, and then you divide by the probability of B. Okay, and then this denominator, the probability of B, can be found by calculating the numerator for all of the different possible values of A. Okay, so all of the different possible classes of A, or something like if you integrate the numerator across all values of A, or you take the sum across all values of A, then it will equal the probability of B. And so what we want to do is we want to find this conditional probability. What is the probability that the new observation belongs to a certain class, okay, certain class C, given the values in its X variable, okay, along with all of the training data. Okay, so this big X and T over here represents all of our training observations, our training values X and our training labels at T. But basically we want to know, all right, if we're shown this, the new values of X in our new observation, what is the probability that it belongs to a particular class? And so, it's a probability, so we're going to get rules, it's going to be a value between 0 and 1. And then when you add up all of the probabilities, they have to add up to 1. Okay, so as I said, if you have ABC, you might get 19%, 80%, and 1%. So the way Bayes' rule is going to get applied, okay, so basically the part we want, the A part, is what is the probability it belongs to a certain class, and then the given part B is basically our values in X, okay? And so this is going to be found by finding the probability of X given C, all right? This part is what we call the likelihood. And so basically we are going to kind of create a distribution of what X is for each of the different classes C, okay? So it's the probability of observing the values in X if we assume the observations belong to a specific class C. And so, just a overly simplified example, let's say you're trying to guess, what is someone's gender based on the height, okay? And so X would be the person's height, C would be, person's gender. And so we would end up, in order to kind of answer that question, we would have basically, what is the distribution of heights for men? What is the distribution of heights? What is X for women? Okay, whatever classes you have, you might have this, okay? And then, given those different distributions of X, okay, now that we see an X, we can try to guess, right? And this is not going to be a very good model, but the general rule of thumb is that if an unknown person if the only piece of information we know about this person is that this person is tall, okay, we're going to increase the probability that the person is a man, okay? If the person is short, relatively short, then we increase the probability that the person is a woman. But of course, there's individuals, who are tall or short in either gender, or in any gender, and things like that, and non-binary, and so there's all kinds of things like that. But this is the idea: is we're gonna have to figure out the distribution of X for each of the different classes that exist. Okay, we're going to multiply that by the probability that something belongs to a certain class. Okay, this is the probability that some new observation belongs to class C before we know anything else about this. Okay, and then in the denominator we have the marginal, which is just the probability of observing this particular X value regardless of class label. Okay, and all of these things kind of have this given XT, and this is, all of these values are based on what we've seen in our training data. So, the law of total probability basically says, you can get this by, we know that all of these things have to add up to 1, so we can take this, if we calculate the numerator, this numerator value, and we look at every single possible value that C can be, okay, then this will give us the probability of X regardless of what class label, okay? So we'll say, what is the probability of X for, this possible class, this possible class. We look at all of the possible classes, we add them all up, okay? And so that's what this thing in the denominator is. It's just basically saying calculate the numerator across all of the possible values here, right? And the reason why we want to do this is so that the numerator, like when we calculate all of these things, when we calculate this divided by this, everything will add up to 1 in the end, right? So if I have 3 different classes, this probability for the different classes will add up to 1. Okay. All right, so we are going to try out just kind of a simple example, and we'll have a probability distribution, different possible classes, and we'll work through this. So we're going to say we imagine that we buy these pouches, and the pouches are filled with marbles, and they come with red marbles and blue marbles, right? And we just order 25 bags from some company online, okay? And I don't know, the bags are labeled with production codes and stuff like that. And so we see, the pouches are filled at 3 different factories, okay? And perhaps each of these factories has a slightly different filling proportion, okay? And so we've got 25 pouches, 24 of them are labeled, okay? And then we're going to try to figure out the last one that's not labeled, okay? And of the 24 that are labeled, 12 of them came from factory A, so half of our bags came from factory B. 6 of them came from factory B, and 6 of them came from factory C. So half of our bags came from factory A, a quarter from factory B, and a quarter from factory C. Okay, so 6 out of 24. And we are going to assume that the bags get filled, via basically a Bernoulli or binomial process, meaning that, each marble is kind of put in one at a time, so that there's no, when one marble goes in, it's not going to influence, or it's not correlated to like the next marble that goes in or something, okay? So, a bunch of different pouches, 24 of them are labeled, 1 is not, and we're going to try to figure out which one, okay? And so we go through and we're going to dump out all of our marbles, and we tally all of these things up. So, we open up one of these bags that came from factory A, and maybe it was, 65% red, okay? And then we open up another bag from factory A, and maybe it was 55% red. We do this with all of the different pouches that come from factory A, and overall, 60% of the marbles that come from factory A are red and 40% are blue, okay? So factory A tends to do 60% red, okay? Meanwhile, we look at the pouches that come from factory B, and after tallying them all up, 50% of the marbles are red and 50% are blue, okay? And then when we look at the pouches that come from factory C, and 40% are red and 60% are blue. So we don't work at the factories, and we don't know the exact filling proportions. We're just assuming that our bags of marbles are representative of what's coming from the factory. This might be a bad assumption, okay? But we're just assuming that what we see in our bags is representative of what's coming from the factory. So therefore, based on the data we've collected so far, if you ask me, what do you think is the proportion of red marbles coming from factory A, we're going to say factory A 60% are red. Okay, at factory C, 40% are red, so on and so forth. Okay, and the pouches do exhibit variation, so that it's not like every single bag that came from factory A were exactly 60% red. Some had more red, and maybe others had less. So it's possible that you have one pouch with 20 marbles that was where 14 are red, so 70% red, and then another one where it's only like 55% red and things like that. But overall, the proportion is 60% red, okay? Because if there was no variation, it would be very easy, right? Like if every single bag from factory A came with 60% red, then we could say, oh, this bag is 60% red. It must be factory A. But we're going to say there's still some variation, okay? The ones that come from factory A, there's still some variation, okay? Okay, so we take our test bag and we open it up and we look at what's inside the test bag. And when we do this, there's 20 marbles and 10 of them are red. So in our test bag, it's 50% red, okay? And so based on what we see in this bag, we want to try to guess which factory it came from. So part of it is going to say, well, okay, let's look at the likelihood of getting our data. We want to know what is the probability of getting our data, in this case, 10 red marbles out of 20 marbles, okay? And we want to know, okay, what is the probability of getting that result if it came from factory A? What is the probability of getting that result if it came from factory B? And what's that result if it came from factory C? So we can say, okay, what is the probability of getting 10 red marbles out of 20 marbles if we came from factory A where the filling proportion is 60%, okay? And so for that, we're going to use binomial probability, right? So that's n choose x, p to the x, 1 minus p to the n minus x. So we're going to do 20 choose 10. The probability of getting red is 60%. We got 10 red marbles. Probability of getting blue is 40%, and we had 10 blue marbles, okay? So it's going to be 20 choose 10, 0.6 to the 10, 0.4 to the 10, and we get a likelihood of 0.117, okay? We do the same for factory B. In factory B, the filling proportion is 50% red and 50% blue. So we do 20 choose 10, 0.5, probability of red, 0.5 raised to 10 because we have 10 red marbles. Probability of blue is 0.5 raised to the 10 because we have 10 blue marbles, okay? And then we also ask what's the probability of getting factory C. Likelihood for factory C is 20 choose 10. And then in factory C, 40% of the marbles are red. So we do 0.4 raised to the 10. And then 60% are blue, 0.6 raised to the 10, because that's what we have. We have 20 marbles, 10 are red, and 10 are blue. So this is our likelihoods. And so based on the likelihood alone, the likelihood for factory B is the highest. Okay, and that makes sense because factory B, 50% of the marbles are red, and when we opened our bag, 50% are red. So that aligns the closest. So based on likelihood alone, factory B has the highest likelihood. But we want to factor in what the prior probabilities. Okay, the prior probabilities showed us that when we first looked at our data, factory A was responsible for half of the bags. Okay, and factory B was responsible for only a quarter, and factory C only for a quarter. So we want to bring that in our prior probabilities. Okay. So before we even opened the bag, I guess we could have asked, like, if you just had to guess based on what we've seen the other bags and which factories they came from, which factory do you think it came from? And so we would say, okay, our prior probabilities for factory A would be 50%, and the prior probability for factory B would be 25%. The prior probability for factory C would be 25%. So I have 0.5, 0.25, and 0.25. Okay. So we combine our likelihood and our prior just by multiplying them together. Okay. So the likelihood this was the binomial probability from back here. So the binomial probability, I'm just going to multiply the likelihood, the binomial times the prior probability of 0.5, okay? And then for class B, I take that binomial likelihood and multiply it by the prior probability of 0.25. And for class C, I take the binomial likelihood of 0.117 and multiply it by the prior probability of 0.25, okay? And so this would be the numerator calculated for our three different classes. So the numerator for class A is 0.058, the numerator for class B is 0.044, and the numerator for class C is 0.029, okay? So effectively, we're like done with the problem, okay? Except the issue is that if I add these things up, these don't add up to 1. Okay, so basically I just have to scale everything up so everything adds up to 1. I want to keep the relative sizes here so everything will add up to 1, and that's why we're going to divide by the denominator. And the denominator is going to be the sum of our numerators. So we take the numerator for all three possible classes and we add them up, and that's going to give us our denominator. So if you do 0.0585 plus 0.044 plus 0.029, you're going to get 0.1319, okay? And this is our denominator. This is basically what is the probability of getting our data 10 red marbles out of a bag of 20, regardless of the class, okay? We want to consider the possibility that it came from class factory A or factory B or factory C. We add them up. Okay, and so the probability of getting this, regardless of which class it came from, is this. And so now I can kind of divide each of these numbers by 0.1319, and this will give us our probability, our posterior probability, the probability that it came from factory A, given that we saw 10 red marbles out of 20 marbles, okay? So our numerator on this page is basically I took the likelihood times the prior probability. So this is the binomial calculation, prior probability to get this number 0.0585. I'm going to divide by this denominator 0.1319. So if I do 0.0585 divided by 0.1319, that's going to give me around 44%, okay? And so I guess this is just to show everything all together. This is the likelihood. What is the likelihood of getting your data? 10 red marbles out of 20, okay? Given if we assumed it came from class A, okay? Class A has a probability of 0.6, and so that probability is this binomial part right here. And then this is the prior probability. What is the probability that it came from factory A? If you didn't know anything else about the bag, and we said, well, out of 24 bags total, 12 of them came from factory A. Okay, so when you do that, you get this 0.0585 divided by the sum of the numerators across all the classes, and we get around 44%. Okay, we do the same for class B and class C, and we get around 33% and 22%. And so therefore, our probabilities is after we open up the bag, the probability that came from factory A is 44%, factory B is 33%, and factory C is around 22%. If you open up a bag where it's 10 red marbles and 10 blue marbles. So our test case was 50% red, okay? And so again, what the Bayes classifier does is it kind of factors in the different pieces of information you have, right? So if we were to try to base our classification only on the information that it was 50% red, we would have picked factory B, because in our training data, factory B produces bags that are 50% red on average, okay? Sometimes a little more, sometimes a little bit less, but on average 50% red, okay? And whereas factory A does 60% red and factory C does 40% red. But the Bayes classifier takes into account the prior probabilities, which said, when we looked at all of our bags, half of them came from factory A, okay? And only a quarter of them came from factory B. So when you take those two things into account, okay, you get something in between, okay? So if you only looked at the proportion of bags, we would have said 50% chance that it came from factory A. But after seeing that the bag was only 10 red and 20 out of 20, that gets dialed down, right? So the prior probability was 50%. After incorporating what we saw in the data, this goes down to 44%, okay? The prior probability for factory B was 25%. After what we see in the data, it goes up to 33%. The prior probability for factory C was 25%, and after looking at inside the bag and seeing the data, it drops down a little bit to 22%. So that's what happens. We're combining our information between our prior probabilities and the likelihood of the data. Okay, let me give you your first UQuiz answer, which is the letter C. C as in cat. So some of the assumptions that we're making that we just want to be mindful of, okay? It says, after tallying all the data in our factory, we assume that the maximum likelihood estimates of the proportions of red marbles at the factory is basically the filling proportion, right? So when we just opened up our bags of marbles that said factory A, we went and assumed that factory A fills marbles at 60% red. And if you have better information, like if you work at the factory and you go, oh no, factory A, we fill at a 50% red, okay? And I don't know what happened with your set of bags. Your set of bags just ended up 60% red. Then we would factor that in, okay? But right now we're just kind of basing our guesses based on what we observe, okay? But I don't know if this is just with a simple example, but apparently you can go to I just saw a video on YouTube about the Haribo gummy bear factories, and they I want to say they fill the red gummy bears at a higher proportion than the other flavors, because that's the most popular flavor. So it's 40% red or something like that. I don't know. But I thought, oh, that's interesting, right? Because I just assumed all of the different colors show up in equal proportion, but that's not the case. And anyway, okay. And then the other big assumption was that, in my sample of 24 bags, 12 of them came from factory A. So I said, oh, factory A is responsible for, half of the world's global marble production or something like that, okay? And again, maybe not a great assumption, okay? And again, if we work for the marble factories or marble company and we go, oh yeah, I actually know about the global supply chain, and I know that factory A and factory B have the same kind of output, and so whatever happened, you ended up with fewer factory B marbles or something. We would adjust all of that, but right now we're just assuming all of this, okay? What would happen if we have a different data set, okay? So here we're going to do the same example, except this time we're going to say when we opened up the bag, it was mostly blue marbles. There were only 6 red marbles out of 20 marbles. So we look at this, and there were only 6 red marbles. And so it's only, 30% red, okay? So we're still going to use the prior probabilities, where 50% came from factory A, 25% came from factory B, and 25% came from factory C. But then my likelihoods will be 20 choose 6, and this is the probability of red, 60%. And how many red marbles did we get? We only got 6 of them, okay? How many blue marbles at 40%? We got 14 of them. And then, and so this number is going to end up being quite a bit small because you're doing 0.4 raised to the 14th power, okay? And so the resulting numerator here is, 0.002, okay? Meanwhile, if we look down at factory C, we do 22.6. What's the probability of a red marble for factory C? It's only 0.4, and we only have 6 of them, okay? And what's the probability of a blue marble for factory C? It's 60%. And how many do we have? We had 14 of them, okay? So this number is going to be not as small as this one, okay? So even though we're multiplying by 0.5 here, and here we're multiplying by 0.25, the numerator for factory C is a lot bigger at 0.03, okay? 0.03 versus 0.002, okay? Same kind of calculation for factory B. This time it's 0.5 to the 6, 0.5 to the 14, and you get 0.009, okay? And so if you add the numerators across all 3 possible classes, this adds up to 0.042, okay? So this denominator is like much smaller than, say, this denominator of 0.1319, okay? And that's just to say we're less likely to get a bag where there's only 6 red marbles than a bag where there were 10 red marbles, okay? So this denominator is, what's the probability of just getting your data regardless of whether it came from factory A, B, or C? We're going to say, the factory doesn't matter. Like, what's the probability of just getting this result? And this is just saying you're not as likely going to see a bag with only 6 red marbles, okay? But if you did see a bag where there were only 6 red marbles, which factory do you think it came from, okay? So if we take our numerators and we're going to divide by our denominator, okay, the resulting probability that it came from factory A is around 6%. The probability that it came from factory B is around 22%. And the probability that it came from factory C is close to 73%, okay? And so I think this makes a lot more sense, or this makes a lot of sense in that, again, prior to looking at our data, we said, well, factory A produces half of the marble bags and factory C only produces a quarter of the marble bags, okay? However, when you opened up the bag and you saw that there were only 6 red marbles out of 20, okay, then factory C became the most likely candidate for making this bag, because factory C fills its bags at only 40% red compared to factory B and factory A, which has a higher, proportion of red marbles. And so, could it have come from factory A? It could, okay? Factory A does produce half of the marble bags after all. And but at factory A, 60% of the marbles are red. So, is it possible that, when you get 20 marbles, just by random chance, you only got 6 red marbles? It's possible. It's not as likely. And so the overall probability that it came from factory A is quite small, at around 0.0567, okay? So the prior probability would have been 0.5. After looking in the bag, it drops down to around 6%. Prior probability for factory B was 25%. After looking in the bag, it goes down to 22%, 20.6%. And then prior probability for factory C was 25%. After looking in the bag, it now jumps up to 72%. Okay, so that's what we have. So getting only 6 red is not unlikely if it comes from factory C with a filling proportion of 40% red. So despite our prior probability that only a quarter of the bags come from factory C, our observed data makes factory C the most probable class assignment. Okay. So that's how the Bayes classifier works, and we can use the same concept of the Bayes classifier and apply it to, just more, I guess, I guess, more interesting data, all right? And so we can look at mixtures of multivariate Gaussians or multivariate normal distributions, okay? So the multivariate normal distribution so this is a joint distribution. And here we have, I guess, multivariate distribution on X and Y. And so properties of the multivariate normal is that if you look only at X, X is normally distributed, okay? And if you look only at Y, Y is normally distributed, okay? And their joint probability, okay, is that, you know, a lot of times you will have some covariance. And here you kind of get these things that look like ellipses, okay, to indicate that there is a joint distribution here. And so this is another kind of plot. This is multivariate normal on X and Y, and what you end up getting is this kind of this hill-looking thing. It looks like a hill. From the top down, it might look like a bunch of kind of ellipses. And yeah, anyway, okay. And then the PDF for the normal distribution looks like this, okay? Which is kind of a, if I look up the normal distribution, the PDF of the normal distribution is this, and the PDF of the multivariate normal distribution is pretty much like the same thing, but just kind of a multivariate generalization of it. So, so let me pull up. So here's the PDF of the normal, and if you look at the PDF of the multivariate normal, you have the same kind of components. You still have the 2 pi in there, okay? And then here, the sigma matrix is kind of like your variance, okay? And we have the determinant raised to the -1/2, which is kind of like the square root on the denominator here, okay? And then you have exp, or e to the, all right? And you have, for the normal, you have x minus mu, basically the distance from your mean squared. And you have something similar, basically, what's the distance between x and your mean vector, okay? Except there's no squaring, but you have x minus mu transpose x minus mu, which is effectively the same thing as squaring a vector, okay? Also raised to the -1/2, raised to the -1/2. And then over here, instead of the variance, you have the inverse of the variance matrix, which is kind of like dividing by the variance there, okay? Because again, in matrices, no division, but you can multiply by the inverse, which is conceptually similar to it, okay? And so anyway, we have this variance matrix sigma, okay? And that's going to be kind of our variance covariance matrix of the different variables in our multivariate normal distribution. Now, the multivariate normal can exist in very high dimensions. You know, when we plot things, because I'm going to be plotting stuff, I'm going to just be using 2-dimensional examples. But yes, you could have these high-dimensional multivariate things, and you know, I guess a 3-dimensional multivariate normal would be kind of like these, I don't know, not spheres, but like egg-like ellipsoids, or I don't know, is that what they're called? Like football-looking things, right? Okay, so anyway, just to kind of show an example, I'm going to just generate data. And when I generate data, I have I'm going to have 3 classes: class A, class B, class C. Class A is going to be centered at 2, 3, so that's going to be upper right. Class B will be centered at 0, 0 at the origin, and class C will be centered at 2, -2, so lower right quadrant, I guess quadrant 4. okay? Sigma A, its matrix is top left corner is 3, the off diagonals are 0, and the lower right corner is 1. So there's no covariance between x1 and x2, so they are independent, and x1 has more variance than x2, okay? For class B, it's the identity matrix. So x1 has the same variance as x2, and there's no covariance, okay? And then class C, we have x1 and x2 both have variance of 3, but then they also have covariance of 2.5, okay? So there's a positive covariance between x1 and x2. So I'm going to generate 30 points from each of these distributions. These are just random points, and I'm going to plot them. And I'm also going to plot kind of these ellipses at the, I don't know, these are the theoretic multivariate normal distributions at the kind of the 40th percentile, 65th percentile, 80th, 90th, and 95th percentile. It's kind of like if you think about the normal distribution, and I say, all right, I want the middle 40%, okay, and then like 0.95, I would get 95% here, and this is equivalent to basically like negative 1.96 and positive 1.96. But now we're, if you have these this normal distribution, it kind of corresponds to these ellipses at these different levels. Okay, and so this is the resulting plot. Okay, so class A is in red, and the origin or the center of its distribution is around 2, 3. Class B is in blue, center is around 0, 0, and class C is in green at 2, -2. And you can see for class B, the variance in one direction is 1, and so this takes me to basically plus or minus that. There's no covariance, and so we have these basically concentric circles because x1 and x2 have the same amount of variance. Okay, whereas class A, x1 has more variance than x2, so we have more spread horizontally, okay, than we do vertically, and they are independent of each other. So the major and the minor axes of these ellipses are parallel to the x1 and x2 axis. Okay. Meanwhile, for class C, there is covariance, and so we basically see positive correlation between x1 and x2, x1 has variance 3 and x2 has variance 3. So we have that. Okay. So this is what our simulated data look like, and these ellipses represent kind of the parameters of the distribution that generates our values. Okay, and but when we are doing our Bayes classifier, okay, we don't actually know the distributions that generated our data. Okay, we're basically just getting our red dots, blue dots, and green dots. They come in labeled, okay, but we don't actually know what is the distribution that generated this, right? So we have to kind of estimate. So we're going to basically just imagine these dots come in, just the dots, no ellipses, red dots, blue dots, and green dots, and we have to try to guess what is the mean of the red population. And what is the mean of the blue population? What is the mean of the green population? What's the variance of the red population and the variance of the blue population and the variance of the green population? So we're gonna have to estimate those. Well, it's rather straightforward. Estimating the mean of, the red population based on the red dots, all we do is we just take the sample mean, okay? It's in 2 dimensions, so you just basically take all of your red dots, all of those values, you take the mean of the x1 column, you take the mean of the x2 column, and that's going to be the mean there. So you're just taking basically your vector x, add them up, divide by how many you have, okay? N sub c is basically how many points belong to class, whatever that particular class is. So we add up our 30 values that belong to class A, divide by 30, and so on and so forth, okay? So here I can just calculate the column means of our XA values and the column means. And so, the distribution that generated our dots was centered at 2, 3, and when we take our sample mean, we get 2.26 and 2.8. So not quite exactly that. Similarly, for class B, the distribution that generated our points should have been centered at 0, 0, and we're getting something a little bit different. And then the points for class C, the distribution that generated our values were at 2, -2, and we're getting something close to, but not exactly that, right? There's natural variance. Meanwhile, as far as the variance goes, we just basically calculate the sample variance for the observations that we have. And so when you have multidimensional data, it's going to be x minus mu times x minus mu transpose. Okay, and this is going to return a 2x2 matrix, and so that's what we have there. Okay, you can kind of do it for each individual observation and add them all up. You can also kind of do it quickly by taking the entire matrix, all right, and doing this minus this transpose. Okay. All right. So the MLE is the average kind of like square distance, but it's like the square difference there. But these will be biased, and so we do divide by n minus 1. And so this is what would happen if you ask the computer calculate the variance of this calculate the variance of this this matrix, okay, 30 rows, 2 columns, this is the estimate it gives you, okay? So that's all we have to do. So we take our 30 observations in XA, so this is 30 rows, 2 columns, and we can just say, hey, what's the variance of this thing? And we get a 2x2 matrix. And so again, the true thing had a variance of 3, covariance of 0, and a variance of 1. So it should have been 3, 0, 0, 1 was what was used to generate it, and we're getting something close to that, but not exactly. For class B, it was the identity matrix was used to generate our values, so we should be getting something close to 1 and something close to 0 over there. And then for observations in class C, we had 3 on the diagonal and 2.5 on the covariance. And so, for whatever reason, we didn't have as much variance in our sample of data. Okay. And so what I'm going to do here is, using these variance estimates and these mean estimates, I'm going to plot what the resulting ellipses would look like. Okay, so you'll see these are kind of more centered on the values themselves, right? So over here, this was the original distribution. We generated blue dots, okay? But because of randomness, they're not exactly centered at 0, 0. And the amount of variance we saw, didn't quite fit it. And so when we replot them, this is like where it's centered versus, and this is, and we can see the variance kind of ellipses fit our values a little bit more closely. Okay. Similarly, this is what we have for the red and what we have for the green. Okay. So if I compare the two, okay, so with the black lines, that's what was used to generate it, and the orange is what we're estimating. And so we're kind of basically going to have to use these orange lines because we don't actually, like in real life, you wouldn't know what distribution generated your data, okay? But this is, this is simulated, so we can kind of pretend. But in generally, this is what you would have. You would have the values, they come in, they're labeled. Based on the labels you see, you're going to estimate the properties of the distributions for each of these classes, okay? Because again, what we want is we want to get a way to calculate the likelihood. If it came from the red class, what's the likelihood of getting this value? Okay, if it came from the blue class, what's the likelihood of getting this value? Okay, so we're comparing that and that. So here's an example. Here's a test case. I'm going to put a dot right at 0, 0. Okay, and so if this is a new test case, and I said, hey, guess what class, or what should we label this observation? I think we would all say, oh yeah, this one should be blue, right? Okay, and but we'll run it through the Bayes classifier, and we want to know, okay, what is the probability it's red? What's the probability it's blue? What's the probability it's green? Okay, so again, red is A, blue is B, and green is C. So we're going to say, what is the likelihood? What is the likelihood that basically a multivariate normal that looks like these orange ellipses, okay, would produce this dot? What is the likelihood that multivariate normal that looks like these orange things would produce this dot, and so on and so forth? So, we use the same thing. We're going to calculate the likelihood, and this is the likelihood of observing the case 0, 0, which is our test case, if we assumed it came from class A or class B or class C. Okay. The prior probability is, if you didn't know anything, right, a third of our dots came from A, a third came from B, and a third came from C. So our prior probabilities is just going to be 1/3 for all of them. If you had some kind of class imbalance and, class A had more observations than some of the other classes, then you would adjust that in there as well. And then the marginal is, what's the probability of getting 0, 0 regardless of class label? And we're going to just calculate the numerator across all of the possible classes there. So as far as calculating the likelihood, we're going to use the multivariate normal density. And so here, our observation is 0, 0, okay, and that we're going to treat that as a vector, and then to calculate this, I would do 1 divided by, and then I have 2 times pi raised to the d is the number of dimensions, so raised to the 2/2. So this is, just raised to the 1. We'll take the determinant of our variance matrix and raise that to the 1/2, okay, times e to the, okay, negative 1/2, and then we're going to take the difference between our x nu, our 0, 0 vector, minus the mean vector for A, okay, transpose times the inverse of our variance matrix, okay, times x minus x bar A, right? So this looks kind of like a mess, but it's really just the multivariate normal PDF put into code, okay? And so this is our likelihood of getting 0, 0 for observation A, okay? And so, it's not observation A, class A. So class A, looking at this, we'd say, oh yeah, it's low likelihood that it comes from class A, and, indeed we have a pretty small number, 0.000879, okay? Now this is a pain, and so thankfully, there is a function called DMV norm, which will calculate multivariate normal densities, okay? But it is, sometimes if you just jump straight to the function, it feels kind of mysterious. And all it is it's doing just the exact kind of multivariate normal PDF. And if you had to do this and turn it into code, this is what you would do, and you get 0.00879, 0.000879. And indeed, if I plug in these, I get the exact same number, 0.000879. Okay, and we're just saying, okay, what is the density for 0, 0 for this mean and this variance? Okay, and so I'm going to do the same thing for class B and class C. And so based on this, we can see, yeah, indeed, class B has the highest likelihood. Class A has a low likelihood. Class C has a very low likelihood. Okay. So these are my likelihood values. My prior numbers are just going to be 1/3 for all. Prior A, prior B, prior C. They're all going to be 1/3 because, at least in this scenario, I have 30 points from A, 30 points from B, and 30 points from C. So, and again, so everything will kind of cancel out. We don't have to, but I'm going to include them in. So the denominator is going to be the numerator, which is our likelihood times our prior, added up for all of the classes. So I have the likelihood of class A times the prior of class A, plus the likelihood of class B times the prior of class B, and the likelihood of C times the prior of class C. Okay, all added up. That's going to be our marginal probability, and then I will calculate my posterior by taking my numerator, likelihood times the prior, divided by the marginal for class A, for class B, and for class C. And so, as one would expect, the probability belongs to class B is the highest at around 99.5%, and there's around a 0.5% of it belonging to class A, and a very, very, very small probability that it came from class C. So looking at this, 95% class B, and yeah, looking at kind of the distribution, we give it a 0.5% probability of coming from class A, and almost a 0%, because again, for the green distribution, the center is here, but if we expect things to be like far away from the center, we expect it kind of be on this axis, or this, I don't know, this line of covariance, and so this is kind of like pretty far off, in the covariance speaking. Okay, so that's what we have for that observation. Okay, here's just kind of another example. This time I'm out at 6,2. So just looking at this, what do you think will be our rankings as far as which one's the most probable and which one's the least probable class? So we'd say red is the most probable, and what do you think is the least probable? Blue, right? Blue is going to be the least probable, and so we run it through. So I calculate the likelihoods using our multivariate normal density function, DMV norm. My x nu is 6,2. I plug that in using my current estimates of the mean and variance for all of these things. The priors are there, and my marginals there, and so yeah, class A is around 79%. Class B is on the order of 10 to the minus 9, and class C is around 20%. Okay, so class A has the highest probability. Here, I'm picking something around here, 5,1, and so now we're thinking A and C are close to being tied. Okay, class B is going to have the lowest probability, so if I do that, so actually class A is around 40%, and class C is around 60%. Class B, indeed, very low probability, 10 to the minus 6 on that one. So yeah, so I guess if you look at it, I guess it's a little bit closer. So 60% probability for class C. And then here I tried to pick one somewhere, and so this one, it could be anybody's, right? It could be red or blue or green. And indeed, if you do this, you get around 30% A, 36% B, 33% C. Okay, so you have different locations, and And so this kind of aligns with what we would think, okay? So, yeah, the probability that an observation belongs to a certain class can be found by using Bayes' rule, and this is what we have. Okay, let me give you your second view quiz. Second view quiz answer is the letter B. B as in bear. B. Okay. We can take the same thing, the Bayes classifier, and especially if you have if you're dealing with the multivariate normal, you can relax something, or you could make what we call the naive assumption, and this actually makes calculating things easier. You make a naive assumption, which is we're going to assume our X predictors are uncorrelated, okay? So when you do the multivariate normal, one of the things is you have to estimate this covariance matrix, okay? You have to estimate this covariance matrix. But if this covariance matrix is diagonal, okay, and your off-diagonal elements are 0, then that means the X variables are independent. And if they're independent, you can factor out your multivariate normal into a product of basically univariate normal distributions. Okay, so to make our life easier, we're going to make, I guess, bad assumptions. Okay, and so this is we say this assumption is wrong, but it's still useful. Okay. And the issue is that trying to estimate the covariance between a bunch of X values can become really hard to do, especially if you have a whole bunch of X variables. Okay, so if you have only two X variables, estimating the covariance might not be that hard. But let's say you have 1,000 X variables, okay, and you only have like 1,000 observations, okay, then you've run out of degrees of freedom, and you won't be able to estimate your the covariances properly there. Okay, so with the naive assumption, we're just going to assume all of the covariances are 0. Okay, this is not going to be a good assumption, but it certainly simplifies our calculations. And it turns out that this bad assumption doesn't negatively impact predictive performance that much. Okay, so yes, it does. Predictive performance will go down, but only a little bit. Okay, and so at least for most cases, right? If you have something where it's very highly correlated, and throwing away that covariance is you're going to be losing a lot of information. Sure, that could be a case, but in a lot of cases, just assuming all the covariances are 0 doesn't negatively impact things. Okay, so this is the multivariate PDF, and this is the univariate PDF, and we're just going to say it's going to turn it into a product. So basically, instead of finding the multivariate PDF of x1 and x2, just find the univariate PDF of x1, find the univariate PDF of x2, and multiply those two together. So just take the product of independent things. Okay, so here's our simulated data from before, and what we're going to do is we're going to just treat everything as univariate. So we're going to take x1 and separate it from x2. So I'm going to just take the mean of column 1 and the mean of column 2. So I've got x1 bar and x2 bar for class A, B, and C. And then I'm going to calculate the variance of each column individually, variance and standard deviation. So I've got the standard deviation of column 1A and standard deviation of column 1 for class B, standard deviation column 2 for class A, and so on and so forth. Okay. And so if we estimate the multivariate Gaussians here, okay, here we're basically assuming there's no covariance, and so you'll see that the major and minor axes of our ellipses are kind of parallel to the x1 and x2 axis here, okay? And so the biggest, so this is, the orange is like if we did estimate the covariances, okay? The biggest difference is for the green class, which had covariance, right? So the green class C has covariance, and so when we do our naive assumption, we're assuming there's no covariance, so we're just assuming there's a variance of 3 in this direction and a variance of 3 in this direction, okay, with no covariance. Whereas with the multivariate, you know, we say, oh, you know, there is covariance, and so we get kind of these diagonal things. Okay, our original data, there wasn't a whole lot of there was very little covariance in the red dots and the blue dots, and so we're not getting a huge difference there. Okay, but we do see a big difference for the green dots. Okay, and so yeah. With the naive assumption, there's no covariance, and so that's what we have. Okay, so let's see what happens if we have test case at 0, 0 again. You know, how is this going to affect it? Okay, so what ends up happening is we're still going to guess blue, but now the probability that it's green is, you know, kind of a lot higher. Okay, so the only thing that's really different is when we calculate the likelihood, we're not going to use the multivariate normal. We're just going to use the product of just independent normal densities. So just instead of dmv norm for d density of the multivariate normal, we're just going to use d norm, the plain old normal density function. Okay, so here I'm going to, the likelihood for A, I'm going to just ask for d norm for x1, and so d norm x1, I take my basically this is 0, and then I take the mean of x1 and the standard deviation of x1, and then I multiply it by d norm for x2. Okay, and I do the same thing for class B and class C. So instead of a multivariate normal, now I just have d norm in doing one variable at a time, okay, and taking the product of these things. Okay, so I get my likelihoods for the different classes. I calculate the prior and the marginal. Priors are all 1/3 again. Marginals, likelihood times the prior, added up across all of our things. And so at the end, we get what? 94% class B, okay? And then class C is now a lot higher at around 5%. So compared to, I think it used to be like 99.5% for class B, and now it's a little bit lower to 94%. And class C used to be like around 0, like 10 to the minus 5 or something, and now it's much higher at around 5%. So we see like the difference it does, but at the end of the day, if you said, hey, just predict which class it's going to be, we would still pick class B, okay? And yeah, so probability that it's 0, 0 is still the highest, but again, because we're ignoring the covariance, now class C suddenly seems like it could be a possibility. Okay. Another application of the naive Bayes classifier is we could use it for, say, like document classification. Okay, and this almost seems trivial, but it is like a handy way. Like if you had to kind of take a document, and if you want to classify it into like, is this document about sports, or is this document about politics, or something like that? You know, here's an article, and if you don't know anything about it, do we have a way to kind of classify different documents? Okay, and so the way we're going to do this is we're going to take each word that we see, and we'll have a count of how many times a particular word appears in the document. Okay, so you might have an article, and you're going to say, okay, how many times does the word I don't know, and basically you have as many X variables as there are words in the dictionary. Okay, so I don't know, let's say you have a vocabulary of, I don't know, 50,000 words. Okay, so then you have 50,000 X variables, and it'll, you know, your first column is like, how many times does the word a appear? How many times does the word aardvark appear? How many times does the word, I don't know what the next word is in the dictionary, but it's like, how many times does that word appear? And, you know, you're going to have a whole bunch of zeros, but then it'll be like, okay, the word, you know, apple appears 3 times. So you put a 3 there, okay? And the word, I don't know. And you just get a count of basically how many times each word appears, okay? And this is why we want to use the naive Bayes classifiers, because if you don't have the naive assumption, then you have to calculate all the covariances between all of the different words. Like, and sure, some certain things are going to have high covariances. Like if you have a document about sports, okay, the words player and team will probably have high covariance, right? If you have articles with the word player appearing a lot of times, then probably the word team will also appear more times, and the word game, right? Player will probably be correlated with game, and so there's going to be covariance. But then if you say like, okay, what's the covariance between player and aardvark? You're going to say, well, probably 0. Okay, you know, trying to figure out the covariance between every possible pair of words. So if you have like 50,000 words in your thing, I don't know, what's 50,000 squared? It's a big number. You have a whole bunch of covariances to calculate. Most of them are going to be 0 or close to 0. Some of them won't be. The naive assumption says, you know what, don't bother calculating any of them. Just assume all of them are 0 and make your life easy. And that's why we're going to use the naive Bayes classifier. Our document classifier for this, we're going to look at how many times each word appears. This is known as the bag of words model, okay? And it's kind of, I don't know, like imagine you have, this is your midterm exam, but just like in a cartoon, you see like the paper shake and then the words fall off the page, okay? And it's kind of, that's the bag of words model, is like you shake the paper, the words fall off the page, and now at the bottom, you have a bunch of kind of words, okay? And so in a bag of words, the order of the words don't matter. It's just how many times, what's the count of each word? My battery's just died. So it's the order of the words in the bag of words model. You lose information about the order of the words. Okay, just the counts, which has serious limitations because the order of words is important, right? So if you have these 2 documents, so a document is basically just, it could be as simple as a sentence, it could be an entire article. Okay, just a collection of words is what we're going to show you. But if you have these 2 documents, like you have it is bad, it is not good, and then another document, it is good, it is not bad, these have opposite meanings. But as far as the bag of words model goes, all we're doing is we're going to count how many times each word appears. And so we say it appears twice, and is appears twice, and bad appears once, and not appears once, and good appears once. Okay? And so as far as these 2 documents go, they are exactly the same document in the bag of words model. Okay, so severe limitation um, with that. However, it's still kind of useful, especially for like document classification. You're usually just looking for like, I don't know, different keywords and stuff like that, okay? So a successful document classifier will require what we call a lexicon, okay? A word probability lexicon. And you'll need one for every possible class. So if you have, if you're going to classify your documents into categories like sports and politics and, I don't know, international news or whatever, right? Like your news organization, and you're going to try to put like different classifications and stuff like that, you're going to need a lexicon with probabilities. And so probably your sports lexicon will have higher probabilities for ball and game and team and score, whereas politics lexicon will have higher probabilities for senator and Congress and government and stuff like that. And international will, I don't know, have higher probabilities for like country and prime minister and stuff like that, okay? So this is just a very, very silly example, okay? We're gonna say there's two possible classifications, and our documents can be about fairy tales, or our documents can be about chess, okay? Just because there is some overlap in the words that might be used. So fairy tales and chess both have kings and queens and knights, okay? But as far as like the word princess, okay, fairy tales will have a probably high probability of having the word princess, and chess will have a very low probability about, an article about chess, probably very unlikely to have the word princess in it, okay? I don't know, rook, that seems like a word that doesn't appear very often in fairy tales, but it does appear in chess, okay? Good, like a good move or a good person, that could appear easily in either, okay? Evil, like usually, if you're talking about chess, you're probably not going to say evil very much, okay? And the word bored, probably not going to appear very often in fairy tales. So this is supposed to reflect the lexicon, okay, of probabilities, okay? And this is, again, just a very, very, very simplified lexicon where we have a vocabulary of, 8 words, okay? And again, a real lexicon probably has thousands, 20,000, 50,000 words or something. You get rid of super common words, like ones that aren't going to help you, like the, is, not, a, okay? Those kinds of words you throw out. We call those stop words. They're not useful, so you just throw them out. But you're still going to have thousands of words in your lexicon. But this is just to illustrate something very simple with a vocabulary of 8 words. So the training part is establishing those lexicons. So once you have the lexicon, you don't really have to do any more training. But training is basically going to take all of the documents that are labeled. You say, I know these documents are about politics. And you just have the computer scan and count up basically all of those words and figure out relative probabilities of those things. Okay? And you say, I know all of these documents are about sports. And so you have the computer scan and do all of these kind of counts. And then that could take a long time, right? Okay, so test case, if this sentence, the evil queen sent the evil knight to capture the princess, okay, do you think this is a sentence that came from a fairy tale or from a chess article? Okay, and if you see things like evil, probably not about chess, okay, and then princess, again, not about chess. So our gut is going to say this is going to be fairy tale. So anyway, we look at the words that we have in the lexicon, and so queen appears once, princess appears once, knight appears once, evil appears twice, okay? We're ignoring any word that doesn't appear in the lexicon. Okay, and so when we say, all right, what is the likelihood for the fairy tale class? Okay, we're going to just treat this as the product of independent things. We're not worrying about the covariance or anything. So we just say, okay, what's the probability of seeing the word queen if it came from fairy tale? So looking at our table, the probability for queen for fairy tale is 0.2. Okay, princess is 0.25, knight is 0.2, and evil appears twice. So we're going to square that, and that probability for evil is 0.11. Okay, so knight is 0.2, princess 0.25. And so our likelihood for our bag of words here is 0.000121. Okay? And then when we do it for chess, we take the same bag of words and we do the same kind of things. Okay, what's the probability of seeing queen in a chess article? 0.2. Knight in a chess article is 0.15. Evil in a chess article and princess in a chess article, evil has probability 0.01, and evil princess is probability 0.01, and that appeared twice, and evil has a probability 0.01 or whatever. Okay, so this thing is what? 1, 2, 3, 4, 5, 6, 7. 10 to the minus 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, yeah. So I think 8. So this is on the order of 10 to the minus 8, and this is on the order of 10 to the minus 4. Okay, so one is, much higher likelihood. Now you could also take into account prior probabilities, which I didn't factor in, but if we wanted to, we could do the priors and calculate the marginal, but basically just comparing the likelihoods, we would say the likelihood for chess is much lower than the likelihood for fairy tale based on this sentence, okay? Okay, whereas this one, queen captures the knight, this is a bit more ambiguous, okay? It could be a fairy tale where the queen captures the knight, okay? Could be chess where the queen captures the knight, right? And so as far as our lexicon goes, we just have queen and knight. And so fairy tale, we have 0.2 and 0.2. The likelihood there is 0.04. For chess, we just take our likelihoods from our table, our lexicon 0.2 times 0.15, and we have 0.03. So our likelihoods here are very similar to each other, 0.03 versus 0.04. Okay. This one I copied and pasted wrong, but it should be, if the queen captures the rook, okay, queen captures the rook here. Now for chess, it's 0.04, but for fairy tale, what's the likelihood of rook appearing in a fairy tale? 0.01. So now this likelihood of this sense is, much lower, 0.002. Okay, so again, just very simple examples of this, but you can imagine this being expanded, much bigger lexicon, a whole bunch of different document classifications, and it can be used as a quick and simple way for classifying documents. This is not going to work well for sentiment analysis was like a popular thing for a while. I don't think it's super popular anymore, but the idea of is somebody giving a positive review or negative review on something. Because of bag of words, you're losing the order of, these have opposite sentiments, and the bag of words is going to classify them the same. But if you just want to pick a category for which a document belongs, I think bag of words and the naive Bayes classifier works well. And again, naive Bayes, we like it because we don't have to calculate what is the covariance between every single pair of word combinations there. Okay, that's it for today. I'm going to wrap up things a little bit early, and let me give you your last two view quiz answers, which are the letters E and A. Third answer is E as an elephant, and fourth answer is A as an apple. Okay, we'll end here. We'll see you guys later.